So the way the technical part of the talk is going to go is I'm going to formally state the definitions of logical induction and some desirable properties of it. We're going to talk a lot about the properties. We have an algorithm and a criterion that implies a bunch of nice properties, and the algorithm satisfies the criterion, so that's nice, and I'll talk about those. And then I'll talk about formalizing the criterion, which is actually harder than, requires more definitions than talking about a lot of its properties. We'll talk about the algorithm a little bit, maybe time permitting, and then I'll switch back to PowerPoint and talk about like some conclusions. So let's get to the formalizing. We're going to choose a language or a formal system of logic, gamma, for encoding statements about variables and computer programs. So who's heard of Peano arithmetic in this room? Awesome. Okay, so Peano, so that was like about 70%. So Peano arithmetic is a language. We're talking about arithmetic, but it turns out that you can encode lots of statements about computer programs in Peano arithmetic and then prove stuff about them. So it's a very expressive language. We want our language to be pretty expressive because obviously we want AIs to be able to like think about computers, I think. Or we want our theory of AIs to include AIs that think about computers. And then this capital lambda is going to be the set of all sentences expressible in gamma. And then a belief state, we're going to define a belief state. That's the state that you're in while you're still thinking about stuff. Is a map from sentences to probabilities that is constant outside a finite set. And I think we've toyed with different definitions where it's constant outside the finite subset or zero outside the finite subset. It sort of doesn't matter. The point is, if you're kind of writing down your beliefs, you're only going to be able to have written out like a finite number of beliefs at any finite time. So think of your belief state as just like a list of probabilities that you've managed to assign to stuff so far. And we don't want to say, at this point in talking about the theory, that your belief state is like whatever you implicitly believe, or your like revealed beliefs or your revealed preferences. They're like things that you've managed to explicitly write down. Because if you define your beliefs to be something that's derived from your preferences or derived from your actions or derived from stuff that's already in your mind, then you're no longer separating the belief and the computation. And the whole point of this framework here is to separate the belief and the figuring out of the belief. So your belief state is just the stuff that you've written down probabilities for. And a reasoning process is just like a sequence of belief states. So at each time step, you like adjust your probabilities to all the sentences that you've seen so far, and maybe you add some more sentences that you have beliefs about. Does that make sense? Cool. Any questions about that? Sweet. So now with this definition, we can say what is a good reasoning process. So some properties you'd like to have for a good reasoning process is that it should be computable, or at least our model of it should be computable. We would like it to converge. We'd like this thing not to be like flip-flopping around forever, changing its mind about stuff. Like we'd like it to be eventually figuring out what it thinks about a thing. So that's convergence. And that means to say that we've got this symbol p sub n of phi. So that means like the probability that you assign at time n to sentence phi, or phi, should I say? I think I'll say phi. And we want, as n approaches infinity, for that limit to exist, and we're going to denote it by p infinity. So it's what you will eventually converge to thinking after forever. You'd like the limit to be a probability distribution. So once you're done computing your belief update at the end of time, you'd like to satisfy the laws of probability, finally. So that's these kinds of rules. And there's this other property that people have talked about that I think is desirable, which is that if you never disprove something, you shouldn't think it's impossible. So if you don't prove it, you shouldn't think it's 100%. So that's what this says. If your logical system doesn't prove something, then you're not going to be 100% sure of it. Does that make sense? So these are some nice properties, and in fact, we knew before Garabrant induction that these properties could be satisfied. A guy named Abram Dembski had an algorithm that satisfied these, and the paper that is sitting in draft form on that table right there shows that those properties are related. So there's a single property that I'm going to call the Garabrant induction criterion, which implies all four of them. So that's kind of nice. It means that it's like intuitively, we were just, as humans, just kind of generating these desirable properties, right? And you might think that the only thing they have in common is that humans want algorithms to have them. But they have another thing in common, which is that they follow from the Garabrant induction criterion. And that sort of validates us as intuitive generators of criteria, that we managed to generate a sort of coherent set of criteria to be satisfied. Us as in humans, like all the people who've been working on this field. It also shows that the properties are feasible because we have an algorithm that I'm going to call logical induction algorithm 2016, or LIA. And I'm putting the 2016 in there because, like, you never know, people are going to update these things. People might pick this up after we're done with it and make it better, and I don't want to steal the name logical induction algorithm forever. Someone else might make it better. So we know that those things are feasible, and also they're extensible. There's a bunch of other awesome properties that follow from the Garabrant induction criterion and are therefore satisfied by the algorithm that we have. So that is the deal. That's like what's going on here. We've got an algorithm that does the purple stuff good. Okay. So here are some properties that the algorithm satisfies. It's actually faster to state the properties of the algorithm than it itself, or even the criterion, but we'll get to the criterion. I just want to, it's kind of like, before I start giving you this like big fat definition of an algorithm or a criterion, it's nice to like care, right? So let me tell you what properties it has. I don't think you should care what the definition of the algorithm is or the criterion before you know what properties it satisfies, because otherwise you'd be like, whatever. So there's this non-dogmatism property, which is that it's like a stronger version of the dogmatism property from earlier, which is that if you have any algorithm that outputs sentences, and it outputs this like infinite list of sentences that are consistent, so no pair of them are contradictory or contradictory with the theory gamma, then there's actually some constant such that all the sentences in that sequence are above probability epsilon. So it's stronger than the earlier property. And here's another strengthening of the earlier property, which everyone loves, Kolmogorov complexity. You can actually say for a given sentence, if it's never disproven, then its probability is going to be at least some constant times 2 to the minus its complexity. So there's a nice relationship between how complicated the thing is and how likely it is. And that's why we call it the Occam bounds, because Occam is the Occam's razor. You should, if something's real complicated, you shouldn't believe it. Well, that's not quite right, because of a real complicated disjunction, you should totally believe that, right? real long disjunctions is probably true. So you need to amend it a little bit. There's some relationship between complexity and believability, and like this is probably the good relationship that you want. And again, these are all talking about the limit, right? These are all talking about the probability distribution that our algorithm will converge to. We're not yet talking about what it thinks along the way. Yeah, question?
Sorry, is that sharp? Do you know?
Is it sharp? No.
Like, well, there's a...
You don't have an example that satisfies.
I mean...
So there's a C here. Yeah, I'm sorry, yeah. So I guess you could take the supremum over all C such that this is true, and then it would be sharp.
Like, the C we can prove it for is probably, like...
Not sharp.
Than, like,
Yeah.
C.
Right. Yep. Yeah, any other questions about these properties, actually? Cool. Where did I gotta rearrange something, because this phone over here should totally be in my left pocket, where my left hand goes. All right. So there's some nice properties. Now here's where it gets exciting, because people have been wanting like math to understand math for ages. Like Hilbert was like, hey, can we like put math on a mathematical foundation? And Gödel comes along and is like, no. And then Pudlak comes along and says, sort of. I don't know if you're familiar. So there's some results that say that logic can sort of believe that it's like sort of trustworthy up to a certain bound. But I think that, well, yeah, these are real cool. So our logical inductor, as we'll call it, or our Garabrant inductor, is going to believe, it's going to come to believe in the consistency of the logical system that it's using. So if we define con n is there is no proof of contradiction using n or fewer symbols in our logical system, then eventually at time step n, our Garabrant inductor believes any algorithm satisfying the Garabrant induction criterion is gonna believe in the consistency of gamma up to that point. And in fact, there's a stronger claim, which is I'm going to call belief in future consistency. You can actually choose any computable function So it could be n to the 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 n, whatever, some crazy function. Eventually, on time step n, our reasoner is going to believe that gamma is consistent up to proofs of length f of n. So this is like an extremely strong belief in consistency, that you can basically pick your favorite computable function, and our algorithm is going to believe in consistency up to that function. So it's very, very strong. And you can view this as self-reflection or reflection on the deductive process that it's using. But here's a more explicit self-reflective property. This is basically, it knows what it knows. So at time step n, for large n, at time step n, a Garabrant inductor knows what its own beliefs are. So roughly speaking, if you have some sequence of sentences that are, I'm going to call this polytime generable. In fact, I've got a definition. We're going to elaborate on this in a later slide. But it's like you have an algorithm that takes in n and spits out a sentence in time polynomial in n. So you've got this polytime generable sequence of sentences, and at time step n, our inductor is going to, if its beliefs are like kind of squarely between a and b, like a and b, between a and b by like this epsilon margin, does that make sense? It's like forgivingly inside the a-b interval. Then it's going to know that its beliefs are actually inside the a-b interval with very, very high probability. It's going to be like almost complete. So it's kind of like saying, if it's between 89 and 91% sure of the Riemann hypothesis, then it's going to be 99.99% sure that it is between 89 and 91% sure of the Riemann hypothesis. It can be quite certain of what it thinks. Yep.
Sorry, asking a question, but when you say no, is that like has a representation of in the algorithm?
Yeah. No, it has written down.
Okay.
On time step n, it has written down, this is my probability already.
So that includes like the regressive form of I know A, I know that I know A,
Yeah.
I know that I know that I know.
Yeah. Yeah.
How do you deal with that?
So at any finite time step, it's only going to have regression up to a certain n. Yep. But like, yeah, at time step large n, it's going to know that it knows some finite number of nodes. Yeah. Yeah. Great question. And so now, when you get self-reflection like this, you've got something that believes in its own consistency. You got something that knows what it knows. This is like ripe, fertile soil for like paradoxes, right? We can, so we should all be getting nervous. But in fact, this thing has like a very strong systemic immunity to the liar's paradox. You can find a sentence that basically it's equivalent to saying, our Garabrant inductor doesn't believe me. Okay? You can write down a sentence that says, pick your favorite rational probability p. You can write down a sentence that is equivalent to saying, I am less than p likely to be true. So p could be like 1%. I am less than 1% likely to be true. And the Garabrant inductor just handles the situation. It's just like, no problem. I know what I'm going to do. It assigns it probability p in the limit. And on the way to the limit, it does this crazy thing where it like is constantly flip-flopping its belief right around probability p so that it's less than p of the time. Yeah? So good. Yeah. So good. All right, I'll just say that again. So you make a statement that says, I am less than p likely to be true. I'm going to say p% because it fits natural language better. Okay, so I am less than p% likely to be true. And then over time, its beliefs about that statement converge to probability p. But they like over time, they like oscillate just around p, so that they are actually less than p% of the time. And they're actually, so it works out. Yeah. So you don't get a paradox, and it's awesome. I just cannot. Yeah, and in fact, people are already like seeing what happens when like agents that try to make themselves unpredictable by like trying to, like you can make an agent from a Garabrant inductor that tries to make itself unpredictable by first trying to predict its own actions, and then having a plan that if it can predict its own actions, it will do the opposite. And by virtue of that counterfactual plan, it can't be predictable. And then you get random behavior. Okay, anyway, it's real cool. So Large paradox resistance is real cool. And moreover, you can go so far as to say that this thing kind of trusts itself. So this is another, these are properties like that Miri has been sort of pining for like years, you know, just like how can we have a model of an agent that like trusts itself, trusts its future self, understands itself, knows what it knows, etc. And this algorithm just like does it all. It trusts its future self in the following sense. We have a result that is roughly interpretable in quotes. Those are human quotes, not Gödel quotes. These are the Gödel quotes. And those are the human quotes. So we have a result that roughly says that the that should be a sub n there. Apologies. But the probability at time step n that you assign to a statement phi sub n. Again, sorry, I'm assuming that we've got this sequence of polytime generable sentences. And I'm going to harp on the meaning of those, I think coming up soon, yeah. And the next slide is going to like harp on how important that polytime general thing is. We got some sequence of questions we're asking the inductor that's polynomial time generatable, or generable. And roughly speaking, it has some property like this, that the probability that it assigns to phi, given that its future self, so f of n is some large number, given that its future self assigns probability at least p, is at least p, asymptotically. So this is like saying, if future me thinks that, you know, we're 90% likely to live on Mars, then I'm 90% likely to think we're going to live on Mars, because future me is smart. He's had more time to think. So conditional on future me believing X, I believe X. Yep.
Given that you don't know what future me is going to believe, what explanatory power, why?
Right, so why is this, so this property is good because you want this thing to be able to reason about hypothetical actions it might take. Like, right? Like if someone says, Critch, don't go to Berkeley because the cognitive science department is going to like suck you in and you'll never do math again. I'm like, well, if future me thinks cognitive science is a good field of study, it's a good field of study. So I'm just going to go to Berkeley and not worry about it. Does that make sense? Like I have this confidence that if future me thinks it's a good idea, don't worry, right? So if future me thinks something is true, yeah, it's probably true.
Knowing what future me thinks implies current.
So this is conditioning on what future me thinks. It's different from knowing. It's like, suppose future me thinks it's at least probability p, then it's probably at least p. This is a conditional probability.
And the thing that updates the condition, like to get to the future state, that's the definition of the inductor?
Nope. The cool thing is the inductor is an algorithm. Step 1, it's an algorithm. Step 2, algorithms can be written down formally mathematically. Step 3, this algorithm has beliefs about every mathematical statement, including statements about itself. So you can just write down this statement. That's what the Gödel quotes mean. It means like mathematically represent the statement future me assigns at least probability Pn, and then ask it, conditional on that, what do you think the probability is? And it's like, well, at least that. Now, this is in quotes because it's not quite true. For example, there are denominators, like things could go to 0. It's a bit tricky. So the actual result looks like this. And there's a bunch of definitions that I would have to say to make that true. But you can like just stare at it a little bit, get a sense of the shape of it. You laugh, but I mean, this is how, I don't know, when I read a paper, the first thing I do is figure out the shape of, you know, the results in it. So it's something like there's some indicator function for whether this thing is true, and you multiply the binary variable that indicates whether this thing is true by that thing. And then you take an expected value, which I haven't defined at all, but there's expected values of logically uncertain variables, which is cool. So anyway, there's some kind of future trust thing going on here, which is really great because we really wanted agents that can like reason about their future, and like these hypotheticals where it thinks its future, like it's not gonna try not to go to Berkeley because it's afraid of getting sucked into cognitive science. You know, it's gonna be like, well, future me thinks that's a good idea. It is. Questions about that, actually. This is like, maybe it's kind of deep. Maybe we should have I see lots of like faces doing that. So maybe I should just let you guys do some logical induction right now before I present you more.
Yeah, maybe some of the confusing could be just like whether you're actually endorsing this as an actual thing for humans to
Oh. No, I'm right. I see. Yeah. So I'm not telling you to like buy lots of addictive substances and put them in your house and trust that future you will make good judgments about them. Thank you. Yes. Yes?
Like super crude, just pattern matching. That looks sort of like Cauchy-Schwarz, but the other way around. Is there something weird going on?
There is, yeah, there are like, there are these like sequences of like bounds on stuff that are really what's going on. Yeah, for some values of what you meant, you could be right. Yeah.
Like you can think of that as like Bayes' theorem, where the denominator has been multiplied. Well, not Bayes' theorem, but like the definition of conditional probability.
Yeah, and you like multiplied this thing over.
Okay.
Yeah, but again, I just wanted to let you stare at it. If you want to know more, you have to go to the paper. It's right there. Okay, so that one probably, I don't know quite yet. I was at a math camp with these guys, so I don't really know what's in the abridged version yet, because it got cut down while I was like away. But you notice I keep bringing up these like polynomial time generable questions, right? So hopefully you care now when I give you this definition, because you've been like irritated with it for a while already. The interesting thing about sentences that are generable in polynomial time is that they're easy to generate relative to like other more complicated complexity classes, but they can be arbitrarily hard to answer. So there are polynomial time algorithms that can write down questions or statements of uncertain truth value that are just like, I want to say uncomputably hard to verify, but what I really mean is harder to verify than any computable function of the sentence number.
So like
say again?
like humans?
I don't know if humans were generated in polynomial time, actually.
That sentence might in fact be an example.
Well, I don't know if you use polynomial time to generate it.
An example would be like busy beaver of n is greater than 1, busy beaver of n is greater than 2.
Well, here's one. Here's an example in the next slide. So if you let g of n be the statement, there is no proof of g of n in fewer than f of n characters. Pick your favorite giant function f, okay? And then make a sentence that says, this sentence cannot be proved in under f of n characters for each n. Now, you might wonder, how can you make a sentence that refers to itself? That's a trick called Cantor's diagonal lemma. And actually, there's a version of it that lets you have this parameter n in it. So just trust me, you can look up in Boulos. There's ways of like actually writing down sentences that are provably equivalent to these self-referential predicates. And you can see if gamma is consistent, it's not going to be able to prove this in fewer than f of n characters. All right, suppose that I've got a sentence that says, I'm not provable in less than 1,000 characters.
No, I get it.
Okay.
The implication is then you have something that basically says this cannot be proven.
Well, it just says you can't prove me in under 1,000 characters. You can prove it in 1,001 characters all day if you want.
Oh, okay.
Yeah.
But then you still haven't proven. You can't prove it. You can't be proven.
After 1,001 characters, you've proven that thing is true. This thing is true. There's a proof of it.
Yeah,
But it needs to be very long. Think about it. Do logical induction. All right. So this statement is true, right? If gamma is consistent, this statement can't have a proof, a short proof. And that's what it says. It says, I can't have a short proof. So that makes it true. So, and in fact, because the proof, you can actually write down an algorithm that will search for a proof of this. That algorithm will provably terminate. So there is a proof of this thing. And it, at the very least, at the very most, as long as like an exhaustive search of all strings up to whatever length you need to prove it. Which is not f of n, could be much bigger than f of n. But this thing has a proof. It's true, but its proof is crazily badly long. Does that make sense? But it's very easy to write down. You write this down in log n time. You can actually write down a template for this sentence and just like keep substituting in longer binary strings for n, right? And then this thing just gets crazily hard to verify. And you can roughly see that. So nonetheless, we have this amazing property called provability induction. And provability induction says that if you can generate questions, if you can generate statements in polynomial time that are provable, it doesn't matter how awfully long their proofs get, a Garabrant inductor is going to catch up to your sentence generator and start believing the sentences as soon as you generate them. This warrants pause. Okay, I'm gonna like draw a like kind of cartoon depiction of this thing because I think it's this is a problem. This is a property that we were not looking for that we just got. It just showed up and we were like, whoa, really? Or at least I was just like, what? So we've got our sentences, phi sub 1, phi sub 2, phi sub whatever, and they're all provable, but we're just like crazily badly long proofs. So at time step 1, imagine our Garabrant inductor looks at sentence number 1. So imagine the Garabrant inductor is running along over here, and like Ramanujan is like running along over here generating his super hard to verify conjectures. Okay? And Ramanujan spits out phi sub 1, and Garabrant inductor is like, man, I don't fucking know. 50%. I don't know if that's true. So then at time step 2, it still has a belief about phi 1, and it's like, I don't know. It's hard. I don't get this thing. And then it also has been asked another question, which is phi sub 2, and it's like, yeah, I don't know that either. Okay, just let me think, please. Okay, so these sentences are like coming on. There's this like onslaught of conjectures, phi sub n, right? These mathematical conjectures that are presumably being generated by some like intuitive algorithm that uses heuristics to generate true things, or maybe some like concoction like I just made that's guaranteed to be hard. And eventually one day, you know, at time step like, you know, 10,000, it's like, whoa, hang on, guys. That was true. I figured it out. All right, so it's like 100%, or like something very close to 100. And then you're like, all right, so it's finally caught on to the first thing. It believes the first thing, and then you're like, what about the second thing? And it's like, I don't know. That's still, I'm thinking about it. Okay, so it's still like roughly 50%. And then like much later, maybe at like p a million, it starts to believe both the first and second sentences. 10 to the 6 I should have there. Does that make sense? By time step a million, it has managed to verify like the first 2 sentences, and it's still super uncertain about these ones. So this looks doomy, right? It's like, it looks like the number of sentences it has to consider, right, is like is like getting linearly wide, but like the difficulty of verifying them is like super narrow, right? So it looks at this tiny little cone of things it's going to believe, but no. One day this just stops and it catches up so that like time step super large n, I don't know, maybe it's a Google, I don't know how big a number you need. It's going to depend on the particular algorithm, but it's actually going to catch up and just believe, it's going to widen out, and it's going to believe even statement number n as soon as statement number n gets generated.
I'm sorry, what assumption were you making about the generating process of the student?
It's polynomial time in n. So at each time step n, there's an algorithm that spits out a new sentence, and its runtime is polynomial in n.
Assuming that it's filling in a template.
I mean, it's assuming they're similar in some way. I guess.
Yeah, they're following some kind of pattern, exactly. So it learns that pattern. Yep.
So just to clarify, these are like provable statements that you're feeding, like.
Right, you've got some algorithm for spitting out statements that happen to be provable. They're not quite they don't have to be quite a template in the predicate sense. Like they don't have to be a first order predicate with an n in it, and you keep plugging in different n's. The nature of the sentence could look very different, but they do have to have something in common, which is that there's a single polynomial time algorithm that's generating them, and the point is that it catches on to that pattern. If there's a pattern that it can catch on to, then it does. Yep.
Does it automatically assign the last one 100%?
Like very close to 100%.
Okay, but not actually 100%.
Yeah, for every epsilon, there exists a large n.
It's not like eventually always.
Yeah, well, this is the statement right here, right? So for every epsilon, there exists a large n, such that on time step n, it assigns probability very near 1 with an epsilon. Yep.
So does your inductor like know that it's being like? Wait, so it doesn't.
No, it doesn't know that someone's out there with an algorithm. It might. Induction. Yeah, it figures it performs induction. Yeah. Yeah. Unfortunately, mathematical induction was a term already taken to refer to deduction. So we had to call this something else. Yep.
A little bit later about how information enters the system, but like say that's
in this system right here that we're examining, there's no information entering it. Yeah. This is all in between, like, I've received some data, I've written down some facts about the data, and now I'm like thinking about the consequences of those facts. No new information. Yeah. That's the whole point of this framework. Yep. You could make modifications where you like throw in extra information while it's thinking, and that'd be like future papers, but like we're well prepared to like have versions that do that. Yeah.
So does all of this apply only when the polytime general sequence are all proof statements or proof?
When they're all provable. Now, great question. So what happens if like half of them are provable, right? Yeah, so it does a great job then too. So let me get to that. So we're going to have lots of limits. So we made this notation. This sequence is like roughly the same as this sequence, means that their limit difference is 0. This is a common notation for asymptotics. This one's like roughly bigger than that one if asymptotically the limit of the other one minus the first one is, or second one is 0 or more. So the situation where the inductor catches up to the pattern that's generating the questions, we're going to call that assigning its beliefs in a timely manner. Like this is the timely belief, you know. At the time that you might ask it the question, the belief it assigns at that time is its timely belief. It's the one that it managed to generate on time when the question is made. Who's the next person in this room, by the way?
I'm not sure. You have about 8 minutes. I can look it up deeper.
Cool. Thanks. So there's this another cool property, which probably this will be the last cool property that we'll be able to say in detail, but it says if you have a polytime generable sequence of statements, then if the logical inductor is going to converge to some pattern of probabilities that it assigns to those statements that is also polytime generable, then actually you don't have to wait till infinity. It's going to start assigning those probabilities in a timely manner. So anything that it's any polytime pattern that it's going to believe at time infinity, it's actually going to believe along this diagonal here eventually. So you can prove lots of cool stuff by first proving it using p infinity and then saying, and now there's a large n where it works. So now I have to.
4 minutes, there's a 40-minute break.
Cool.
And if you want to take more questions, you can go to the Poly West room.
Great. So what I'll do is I'll conclude in such a way that people feel comfortable leaving the room for a break, and then I can stick around during break and answer more questions. So.
Take people to the Poly room.
Oh yeah, we can't have break in here?
No, because they can come and set up the next thing.
Got it. Makes sense.
We just migrate.
Makes sense. I'll just bring my laptop. All right. So you know, there's this question of like what happens if half the sentences being generated are true. We have theorems that say, you know, that it at least does well. So it might actually figure out which ones are true. So it doesn't have to say 50%. It just says these ones are true and these ones are false. But if it can't do that, then it says 50%. And we need to define what it means to can't be able to do that. But if it can't figure out the pattern and it falls back to using probabilities, it learns to be coherent. We had a theorem that says that it's coherent at time infinity, meaning it satisfies the laws of probability theory. But actually, you can write down what it means to satisfy a law of probability theory and show that it approximately satisfies laws of probability in a timely manner, like on this diagonal for large n. So there's a bunch of nice properties. They're in the paper. They're going to be more and more papers. And so the formalization of the algorithm is basically finance. You just make a stock market of traders that are betting on the sentences, then you imagine that market, and then whatever the market believes, you believe that. So the algorithm is actually very simple, and the criterion is very simple to state, which is part of what makes it so beautiful. It basically, the Garabrant induction criterion, the single criterion that implies all those myriad lovely properties, basically there's some definition of trader, which warms my heart because I used to be a trader. And it says that you are good at logical induction if any trader who's not willing to plausibly risk losing more than a bounded amount is not going to be able to make infinite money from you. So if you walk up to a Garabrant inductor and you promise yourself you're never going to risk losing more, like going negative $1 million in debt, if you promise yourself that, you're not going to make $1 million betting against it. That's just the definition. And from that one definition, you get all those amazing properties. So pretty cool, I think. And we have the algorithm. I think it's a financial solution to the computer science problem of metamathematics. And time permitting, I will use a whiteboard to answer stuff. So probably I'll take the whiteboard out to whoever it is that I would be able to field questions. And what does all this mean? So switch from Beamer to PowerPoint. So my summary of what I think just happened at MIRI is that we had rational choice theory We had a concept of an agent in it called von Neumann-Morgenstern agent. We had some nice axioms that implied that type of agent. We had nice arguments for why those axioms are important. If you don't satisfy them, you lose a bunch of bets, right? And then we have like various formalized versions of V&M agents. Some where the utility functions are reinforcement, some that aren't. Then we have probability theory. Again, we have a notion of an agent, some axioms that you need to satisfy. Some like arguments that say those are good axioms, right? If you don't satisfy them, you lose money. And then we have like a formal thing called Solomon induction that just does Bayesian updating. And you know it's possible to do computably because there's this thing. So now we have another row to the table. We've got logical uncertainty theory, which can be used to like implement probability theory, which can be used to implement rational choice theory. We've got an agent concept called a Garabrant inductor. We've got arguments that say Garabrant inductors are like good reasoners. We know that they can exist because we have this algorithm that does it. And we don't actually have this yet. We don't have, so that's like open field of fertile inquiry for lots of math people to try and figure out like what would be the analog of these axioms that would like imply like some nice modest conditions that seem like, oh yeah, you could totally satisfy those. And then it turns out if you totally satisfy those, then you happen to satisfy like the big strong Garabrant inductor criterion.